you will be introduced to electrical and electronic components. These components include circuit protection devices, switches, relays, variable resistors, diodes, and different forms of transistors. Today's technician must comprehend the operation of these components and the ways they affect electrical system operation. With this knowledge, the technician will be able to accurately and quickly diagnose many electrical failures. To be able to properly diagnose the components and circuits, the technician must be able to use the test equipment that is designed for electrical system diagnosis. In this chapter, you will learn about the various types of test equipment used for diagnosing electrical system. Electrical components. Electrical circuits require different components depending on the type of work they do and how they are due. A light may be wired directly to the battery, but it will remain until the battery drains. A switch will provide for control of the light circuit. However, if a variable dimming of the lighting is required, a rheostat is also needed. There are several electrical components that may be incorporated into circuit to achieve the desired result from the system. These components include switches, relays, buzzers, and various types of car anti-theft and basic security systems. Electronic cruise control systems. Cruise control is a system that allows the vehicle to maintain a present speed with the driver's foot of the accelerator. Most cruise control systems are a combination of electrical and mechanical components. Memory seats. The memory seat feature allows the driver to program different seat positions that can be recalled at the push of a button. The memory seat feature is an addition to the basic power seat system. Most memory seat systems share the same basic operating principles, the difference being in the programming methods and the number of positions that can be programmed. Most systems provide for two seat positions to be stored in a memory. An easy exit feature may be an additional function of the memory seat that provides for easier entrance and exit of the vehicle by moving the seat all the way back and down. Some systems also move the steering wheel up and to full retract. Electronic sunroofs. Some manufacturers have introduced electronic control of their electric sunroofs. These systems incorporate a pair of relay circuits and a timer function into the control module. The motor rotation is controlled by relays that are activated according to signals received from the slide, tilt, and limit switches. Anti-theft systems. The anti-theft system is a deterrent system designed to scare off would-be thieves by sounding alarms and or disabling the ignition system. This screenshot illustrates many of the common components that are used in an anti-theft system. These components include an electronic control module, door switches at all doors, trunk case cylinder switch, hood switch, starter inhibitor relay, horn relay, and alarm. In addition, many systems incorporate the exterior lights into the system. The lights are flashed if the system is activated. Some systems use ultrasonic sensors that will signal the control module if someone attempts to enter the vehicle through the door or window. The sensors can be placed to sense the parameter of the vehicle and sound the alarm if someone enters within the protected parameter distance. Automatic door locks. Automatic door locks (ADL) use a passive system to lock all the doors when the required conditions are met. Many automobile manufacturers are incorporating automatic door locks as an additional safety and conveyance system. Most systems lock the doors when the gear selector is placed in drive, the ignition switch in run, and all the doors are shut. Some systems will lock the doors when the gear shift selector is passed through the reverse position, while others do not lock the doors unless the vehicle is moving 50 miles per hour or faster. The system may use the body computer or a separate controller to control the door lock relays. The controller or body computer takes the place of the door lock switches for automatic operation. Keyless entry. The keyless entry systems allows the driver to unlock the doors or detect like trunk from outside of the vehicle without the use of a key. The main components of the keyless entry systems are the control module, a coded button keypad located on the driver's door, and the door lock motors. Some keyless entry systems can be operated remotely. Pressing a button on a handheld transmitter will allow operation of the system from distance of 25 to 50 feet. Recently, most manufacturers have made available systems of remote engine starting and keyless start. These are usually designed into the function of the remote keyless entry system. Passive restraint systems. Federal regulations have mandated the use of automatic passive restraint system in all vehicles sold in the United States after 19th. Passive restraints are one of that operate automatically with no action required on the part of the driver or occupant. Airbag systems are on all of the today vehicles. The need to supplement the existing restraint system during frontal collisions has led to the development of the supplemental inflatable restraint or airbag systems, ABS. A typical airbag system consists of sensors, a diagnostic module, a clock spring, and the airbag module. Batteries. A good supply of electric power is necessary for modern vehicles. The engines require a large current to operate the starter motor, and many other systems are electrically powered. All modern cars use a 12-volt system. The majority of vehicle batteries are of conventional design, using lead plates in a dilute sulfuric acid electrolyte. These features leads to the common description of lead-acid batteries. The output from a lead-acid battery is a direct current, DC. A rechargeable battery is an electrochemical unit that converts an electric current into a modified chemical compound. This chemical reaction can be reversed to release an electrical current. The modified chemical compound in the batteries which is available as electricity when connected to the circuit. A few batteries have open cells that require routine maintenance to the electrolyte level. This usually consists of adding distilled water at regular intervals. Most modern lead-acid battery designs have improved plate constructions and the case design, which with precise alternator charge control allows maintenance-free types to be used. A vehicle 12-volt battery is made up from 6 cells. Each lead-acid cell has a nominal voltage of 2.1 volt, which gives a value of 12.6 volt. 12.6 volt, not 20, I'm sorry. For a fully charged battery under no load condition. The 6 cells are connected in series internally in the battery with lead bars. The cells are formed in the battery case and are completely separate from each other. Each cell has a set of interleaved positive and negative plates kept apart by porous separators. The separators prevent contact of the plates, which will give an internal short circuit and affect the chemical reaction in the battery cell. The cell plates are supported above the bottom of the case. This leaves a sediment trap below the plates so that any loose material that falls to the bottom does not cause a short circuit between the plates. The cell plates are formed in a lattice grid of lead antimony or lead calcium alloy. The grid carries the active material and acts as the electrical conductor. The active materials are lead peroxide for the positive plate and the spongy lead for the negative plate. When a battery is in charged state, the positive of plates of lead peroxide are reddish brown in color, and the negative plates of spongy lead are gray in color. When the battery is discharging, a chemical reaction with the electrolyte changes both plates to lead sulfate. Applying an electric current to the battery reverses the process. The charged battery stores chemical energy. This can be released as electrical energy when the battery is connected into a circuit. The electrolyte is dilute sulfuric acid, which reacts with the cell's plate material during charging and discharging of the battery. Sulfuric acid consists of hydrogen, sulfur, and oxygen. These chemicals separate during the charge and discharge process and attach to the cell plate active material or return to the electrolyte. During discharge, the sulfate combines with the lead to form lead sulfate. The oxygen into the positive plate is released to the electrolyte and combines with the hydrogen that is left to form water. During charging, the reverse process occurs with the sulfate, leaving the cell plates to reform with the hydrogen in the electrolyte to produce sulfuric acid. Oxygen in the electrolyte is released to reform with the positive cell plate material as lead peroxide. Near the fully charged state, some hydrogen and oxygen may be lost as gas from the battery vent. Some water can also be lost by vaporization in hot weather. With older batteries, this meant that battery electrolyte needed a regular inspection and topping up. Only water is lost from the battery, and therefore only water should be used for topping up. Any contaminants will affect the chemical reaction in the battery and therefore the performance. Only distilled or specially produced topping up water should be used. Tap water is not suitable for topping up a battery. Acid should never be used, as this will strengthen the acid solution and alter the chemical reactions. Most modern batteries, however, include vapor traps and other features to minimize water loss and therefore need little or no attention. The electrolyte chemical composition changes with the state of charge. It is possible to measure this change using a hydrometer. Sulfuric acid is denser and provides greater buoyancy than water. This property is called specific gravity or relative density. Water, which is used as the basis for measurement of all liquids, is given a value of 1 for readings at 50 centigrade. The dilute sulfuric acid of the electrolyte of a fully charged battery cell has a reading of 1.280. The reading for a half-charged battery cell is 1.2, and for a fully discharged battery is 1.150. As most batteries are sealed to the voltage of the battery can be used to indicate battery condition. A fully charged battery will give a reading of 20.6 volts and the discharged battery 20.0 volts. Measurement of battery condition by heavy-duty discharge should only be carried out on a fully charged battery. Heavy-duty discharge is carried out with a specialist item of equipment. This consists of connecting low-value resistor in circuit with the battery for a few seconds and measuring the value drop. This test applies a load similar to that of the starter circuit. In general, the voltage should not fall below 10 volt. Battery performance can be determined by its ampere-hour rating, but this is also affected by the ambient temperature. A cold battery will have a poor performance in a comparison to a warm battery. A more useful measure of battery performance is its reserve capacity rating. This refers to the time taken in minutes for a battery to discharge to a cell voltage of 1.75 volt when supplying a constant current of 25 ampere. This test reflects a typical current draw for a vehicle that will be needed if the charging system failed during night driving. The reserve capacity of 40 ampere-hour battery will be approximately 60 minutes. Another measure is the cold cranking amps rating, which is a measure of the maximum current that can be supplied for a period of 30 seconds before the battery voltage falls below 7.2 volt. This is carried out of minus 80 centigrade, so that is represent the most severe condition of cold engine starting. The cold cranking maps CCA rating of a battery is an important measure in regions that suffer very cold winter temperatures. Some maintenance-free batteries incorporate a built-in hydrometer to indicate the state of charge and the condition of the battery. The hydrometer is color-coded, which is a green color indicates that the battery is charged and serviceable. A green-black or black color indicates that battery requires recharging. A yellow color indicates that battery is faulty. Where a yellow hydrometer is showing the battery should not be recharged or tested, and the use of jump leads for starting should not be carried out. A new battery should be fitted and the alternator checked for a correct operation. Battery charging can be described as slow or fast. Slow charging is best, but in an emergency a fast charge is acceptable. When recharging, a battery should ideally disconnected from the vehicle electrical systems. There are two types of battery charger: a bench charger, which has a current output of up to 10 ampere hours, and the fast charger, which can recharge battery in 30 minutes with a current of up to 50 amps. The charging system. The automotive storage battery is not capable of supplying the demands of the electrical systems for an expanded period of time. Every vehicle must be equipped with the means of replacing the energy that is being drawn from the battery. A charging system is used to restore to the battery the electrical power that was used during engine starting. In addition, the charging system must be able to react quickly to high load demands required of the electrical system. It is the vehicle's charging system that generates the current to operate all of the electrical accessories while the engine is running. The purpose of the charging system is to convert the mechanical energy of the engine into electrical energy to recharge the battery and run the electrical accessories. When the engine is first started, the battery supplies all the current required by the starting and ignition systems. The entire chain charging systems consist of the following components: battery, AC generator or DC generator, drive belt, voltage regulator, charge indicator, ignition switch, cable and wiring harness, starter relay, and lastly fusible link in some systems. All charging systems use the principle of electromagnetic introduction to generate the electrical power. a voltage regulator, controls the output voltage of the AC generator based on the charging system demands by controlling field current. The battery and the rest of the electrical systems must be protected from excessive voltages to prevent early battery and electrical system failure. Regulation of the charging system is very important. Also, the charging system must supply enough current to run the vehicle's electrical accessories when the engine is running. Automobile computers. A computer is an electronic device that stores and processes data and is capable of operating other devices. The use of computers on automobiles has expanded to include control and operation of several functions, including climate control, lighting circuits, cruise control, anti-lock braking, electronic suspension systems, and electronic shift transitions. Some of these are functions of what is known as body control module, BCM. Some body control module systems include direction lights, rear window defogger, illuminated entry, intermittent wipers, and other systems that were once thought of as basic. A computer processes the physical condition that represent information, data. The operation of the computer is divided into 4 basic functions: input, processing, storage, and lastly, output. Vehicle communication networks. Most manufacturers now use a system of vehicle communication called multiplexing, MUX. They allow control modules to share information. Multiplexing provides the ability to use a single circuit to distribute and share data between several control modules throughout the vehicle. Because the data is transmitted through the single circuit, bulk wiring harnesses are eliminated. Vehicle manufacturers will use multiplexing systems to enable different control modules to share information. A MUX wiring system uses bus data links that connect each module. The term bus refers to transporting of data from one module to another. Each module can transmit and receive the digital codes over the bus data links. The signal sent from a sensor can go to any one of the modules that can be shared by the other modules. Electronic accessory systems. With the growing use of computers, most systems can be controlled electronically. This provides for improved monitoring of the systems for proper operation and the ability to detect if a fault occurs. Electronic cruise control systems. Cruise control is a system that allows the vehicle to maintain a present speed with the drive foot of the accelerator. Most cruise control systems are a combination of electrical and mechanical components. Buzzer or sound generator is sometimes used to warn a driver of possible safety hazards by emitting an audio signal, such as when the seatbelt is not buckled. A buzzer is similar in construction to a relay except for the internal wiring. The coil is supplied current through normally closed contact points. When the voltage is applied to the buzzer, current flows through the contact points to the coil. When the coil is energized, the contact arm is attached to the magnetic field. As soon as the contact arm is pulled down, the current flow to the coil is opened and the magnetic field is dissipated. The contact arm then closes again and the circuit to the coil is closed. This opening and closing action occurs very rapidly. It is the moment that generates the vibrating signal and sound. Some form of circuit protection is required to protect the electrical wiring of a vehicle and to protect the electrical and electronic components. It is now common to practice to protect almost all electric circuits with a fuse. A fuse is the weak link in a circuit. If an overload of current occurs, then the fuse will melt and disconnect the circuit before any serious damage is caused. Automobile fuses are available in three types: glass cartridge, ceramic, and blade. A blade type is now the most popular choice owing to its simple construction and reliability. Fuses are available in a number of rated values. Only the fuse recommended by the manufacturer should be used. A fuse is used to protect the device as well as the wiring. A good example of this is a fuse in a wiper motor circuit. If a value were used that was too high, then it will still protect against a severe short circuit. However, if the wiper's blade froze to the screen, a large value fuse might not protect the motor from overheating. Fusible links in the main output feeds from the battery protect against major short circuits in the event of an accident or error in wiring connections. These links are simply heavy-duty fuses and are rated in such as 50 or 100 or 150 amps. Many types of terminal are available. These have developed from air bullet type connectors into the high-quality waterproof systems now in use. A popular choice for many years was the spade terminal. This is a standard choice for connection relays, for example, but is now losing ground to the smaller blade terminals. Circular multi-pin connectors are used in many cases. The pin vary in the size of 1 to 5 millimeters. With any type of multi-pin connectors, an offset solid or a similar used to prevent incorrect connection. Protect against the corrosion of the connector is provided in a number of ways. Earlier methods included applying suitable grease to the pins to repel water. It's now more usual to use rubber seals to protect the terminals, although a small amount of contact lubricant can still be used. Many multi-correctors use some kind of latching not only to prevent individual pins working loose, but also to ensure that the complete plug and socket is held securely. Cables or wires used for motor vehicles applications are usually copper studs, insulated with polyvinyl chloride (PVC). Copper, besides its very low resistance, it has ideal properties such as ductility and malleability. These make it a natural choice for most electrical conductors. For the insulation, PVC is ideal. It's not only has very high resistance, but is also very resistant to fuel, oil, water, and other contaminants. The choice of cable size depends on the current it will have to carry. The larger the cable used, the better it will be able to carry the current and supply all the available voltage. However, it must not be too large or wiring becomes cumbersome and heavy. In general, the voltage supply to a component must not be less than 90% of the system supply. Cable is available in stock size, but a good rule of thumb guide is that one standard of 0.3 mm diameter wire will carry 0.5 ampere safe. A microcontroller is a compact integrated circuit designed to govern a specific operation in an embedded system. A typical microcontroller includes a processor, memory input-output, and a peripherals on a single chip, sometimes referred to as embedded controller or microcontroller unit. Microcontrollers are found on vehicles, robots, office machines, medical devices, mobile radio transceivers, vending machines, and home appliances, among other devices. They are essential simple miniature personal computers designed to control small features of a larger component without a complex front-end operating system. How do microcontrollers work? A microcontroller is embedded inside of a system to control a singular function in a device. It does this by interpreting data it receives from its input-output peripherals using its central processor. The temporary information that the microcontroller receives is stored in its data memory, where the processor accesses it and uses instructions stored in its program memory to decipher and apply the incoming data. It then uses its input-output peripherals to communicate and enact the appropriate action. Microcontrollers are used in a wide array of systems and devices. Devices often utilize multiple microcontrollers that work together within a device to handle their respective tasks. For example, a car might have many microcontrollers that control various individual systems within, such as the anti-lock braking system, traction control, fuel injection, or suspension control. All the microcontrollers communicate with each other to inform the correct actions. Some might communicate with a more complex central computer within the car, and the others might only communicate with the other microcontrollers. They send and receive data using their input-output peripherals and process that data to perform their designated tasks. What are the components of a microcontroller? The core elements of a microcontroller are the processor, CPU. A processor can be thought of as the brain of the device. It processes and responds to various instructions that direct the microcontroller's function. This involves performing basic arithmetic, logic, and input-output operations. It also performs data transfer operations, which communicate commands to other components in the larger embedded system. Memory. A microcontroller's memory is used to store the data that the processor receives and uses to respond to the instruction that it's been programmed to carry out. A microcontroller has two main memory types. Program memory. Program memory, which stores long-term information about the instruction that the CPU carries out. Program memory is non-volatile memory, meaning it holds information over time without needing a power source. Data memory, which is required for temporary data storage while the instructions are being executed. Data memory is volatile, meaning that it holds its temporary and is only maintained if the device is connected to a power source. Input-output peripherals. The input and output devices are the interface for the processor to the outside world. The input ports receive information and send it to the processor in the form of a binary data. The processor receives that data and sends the necessary instruction to output devices that execute tasks external to the microcontroller. While the processor, memory, and input-output peripherals are the defining elements of the microprocessor, there are other elements that are frequently included. The term input-output peripherals itself simply refers to supporting components that interface with the memory and processor. There are many supporting components that can be classified as peripherals. Having some manifestation of an input-output peripheral is elemental to a microprocessor, because they are the mechanism toward which the processor is applied. Other supporting elements of a microcontroller include analog to digital converter, ADC. An analog to digital converter is a circuit that converts analog signals to the digital signals. It allows the processor at the center of the microcontroller to interface with external analog devices such as sensors. Digital to analog converter DAC. A DAC performs the inverse function of an analog to digital converter and allows the processor at the center of the microcontroller to communicate its outgoing signals to external analog components. System bus. The system bus is the connective wire that links all components of the microcontroller together. Serial bus. The serial bus is one example of an input-output port that allows the microcontroller to connect to external component. The distinction between microcontrollers and microprocessors has gotten less clear as chip density and complexity has become relatively cheap to manufacture, and microcontrollers have disintegrated more general computer types of functionality. On the whole, thought microcontrollers can be said to function usefully on their own, with a direct connection to sensors and actuators, where the microprocessors are designed to maximize compute power on the chip, with internal bus connection rather than direct input-output, to supporting hardware such as RAM and serial ports. Simply, coffee makers use microcontrollers, but desktop computers use microprocessors. Relays. Some circuits utilize electromagnetic switches called relays. The coil in the relay has a very high resistance, thus it will draw very low current. This low current is used to produce a magnetic field that will close the contacts. Normally, open relays have their points closed by electromagnetic field, and normally closed relays have their points opened by the magnetic field. The contacts are designed to carry the high current required to operate the load component. When a current is applied to the coil, the contacts close and heavy battery current flow to the load component that is being controlled. A relay application in a horn circuit. Battery voltage is applied to the coil because the horn button is a normally open type switch. The current flow to the ground is open. Pushing the horn button will complete the circuit, allowing the current flow through the coil. The coil develops a magnetic field which closes the contacts. With the contacts closed, battery voltage is applied to the horn, which is grounded. Used in this manner, the horn relay becomes a control of high current necessary to blow the horn. The control circuit may be wired with a very thin wire because it will have low current flowing through it. The control unit may have only 0.25 ampere flowing through it, and the horn may require 24 or more amperes. Relays can also be used as a circuit diverter. In this example, the high-low wiper relay will direct current flow to either the high-speed brush or low-speed brush of the wiper motor to control wiper speeds. ISO relays. ISO relays confirm the specification of the International Standards Organization for common size and terminal patterns. The terminals are identified as 30, 87A, 87, 86, and 85. The 30 terminal is usually connected to the battery voltage. The source value can be either switched on or off by some type of switch or connected directly to the battery. The terminal 87A is connected to terminal 30. When the relay is de-energized, terminal 87 is connected to the terminal. ISO relays. ISO relays conform to the specification of the International Standard Organization, ISO, for common size of the terminal patterns. The terminals are identified as 30, 87A, 87, 86, and 85. The terminal 30 is usually connected to the battery voltage. The source voltage can be either switched or connected directly to the battery. The terminal 87A is connected to the terminal 30 when the relay is energized. Terminal 87 is connected to the terminal 30 when the relay is energized. The terminal 86 is connected to the battery voltage to supply current to the electromagnet. Finally, terminal 85 provides ground for the electromagnet. Once again, the ground can be switched or unswitched. Solenoids. A solenoid is an electromagnetic device and operates in the same way as a relay. However, a solenoid uses a movable iron core. Solenoids can do mechanical work, such as switching electrical vacuum and liquid circuits. The iron core inside the coil of the solenoid is spring-loaded. When current flows through the coil, the magnetic field created around the coil attracts the core and moves it into the coil. To do work, the core is attached to the mechanical linkage, which causes something to move. When current flow through the coil stops, the spring pushes the core back to its original position. Some power door locks use solenoid to work the locking devices. Solenoids may also switch a circuit on or off, in addition to causing a mechanical action, such as is the case with some starter solenoids. These devices move the starter gear in and out of mesh with the flywheel. At the same time, they complete the circuit from the battery to the ignition circuit. Both of these actions are necessary to start an engine. Resistors. All circuit requires a resistance in order to operate. If the resistance performs a useful function, it is referred to as the load device. However, resistance can also be used to control current flow and the sensing devices for computer systems. There are several types of resistors that may be used within a circuit. These include fixed resistors, stepped resistors, and variable resistors. Fixed resistors. Fixed resistors are usually made of carbon or oxidized metal. These resistors have a set resistance value and are used to limit the amount of the current flow in a circuit. The resistance value can be determined by the color bands on the protective shell. Usually there are 4 or 5 color bands. When there are 4 bands, the first 2 are the digit bands, the third is the multiplier, and the fourth is tolerance. On a resistor with 5 bands, the first 3 are digit bands. For example, if the resistor has 4 color bands of yellow, black, brown, and gold, the resistance value is determined as follows. The first color band, yellow, gives the first digit of value 4. The second color band, black, gives the second digit value of 0. The digit value is now 40. Multiply this by the value of the third band. In the case brown has a value of 10, so the resistor should have 400 ohms of resistance. The last band gives the tolerance, called equals a tolerance range of minus plus 5%. Stepped resistors. A stepped resistor has 2 or more fixed resistor values. The stepped resistors can have an integral switch or have a switch wire in series. A stepped resistor is commonly used to control electrical motor speeds. By changing the position of the switch, resistance is increased or decreased with the circuit. If the current flows through the low resistance, the higher current flows to the motor and its speed increases. If the switch is placed in the low speed position, additional resistance is added to the circuit. Less current flows to the motor, which causes it to operate at a reduced speed. A stepped resistor is also used to convert digital to analog signals in a computer circuit. This is accomplished by converting the on-off digital signal into a continuously variable analog signal. Variable resistors. Variable resistors provide for an infinite number of resistance values within a range. The most common types of variable resistors are rheostats and potentiometers. The rheostat is a two-terminal variable resistor used to regulate the strength of an electrical current. A resistor has one terminal connected to the fixed end of the resistor and the second terminal connected to a movable contact called wiper. By changing the position of the wiper on the resistor, the amount of resistance can be increased or decreased. The most common use of the rheostat is the instrument panel light switch. As the switch knob is turned, the instrument lights dim or brighten depending on the resistance value. A potentiometer is a three-wire variable resistor that acts as a voltage divider to produce continuously variable output signal proportional to a mechanical position. When a potentiometer is installed in the circuit, one terminal is connected to a power source at one end of the resistor. The second wire is connected to the opposite end of the resistor and is the ground return path. The third wire is connected to the wiper contact. The wiper senses the variable voltage drop as it moved over the resistor. Because the current always flows through the same amount of resistance, the total value drop measured by the potentiometer is switches. A switch is the most common means of providing control of electrical current flow to an accessory. A switch can control the on or off operation of a circuit or direct the flow of current through various circuits. The contacts inside the switch assembly carry the current when they are closed. When they are open, current flow is stopped. A normally open switch will not allow current flow when it is in the rest position. The contacts are open until they are acted on by an outside force that closes them to complete the circuit. A normally closed switch will allow current flow when it is in the rest position. The contacts are closed until they are acted on by an outside force that opens them to stop current flow. Simplest type of switch is the single pole, single throw switch. This switch controls the on-off operation of a single circuit. The most common type of SPST switch design is the hinged pole. The pole acts as the contact and changes the position as directed to open or close the circuit. Some SPST switches are designed to be a momentary contact switch. This switch usually has a spring that holds the contacts open until an outside force is applied to close them. The horn button on most vehicles is of this design. Some electrical systems might require the use of single-pole double-throw switch (SPDT). The dimmer switch used in the headlight system is usually SPDT switch. This switch has one input circuit with two output circuits. Depending on the position of the contacts, voltage is applied to the high beam circuit or to the low beam circuit. One of the most complex switches is the ganged switch. This type of switch is commonly used as an ignition switch. In the following circuit, the 5 wipers are ganged together and the wheel moved together. Battery voltage is applied to the switch from the starter relay terminal. When the ignition key is turned to start position, all wipers move the S position. Wiper D and E will complete the circuit ground to test the instrument panel warning lamps. Wiper B provides battery voltage to the ignition coil. Wiper C supplies battery voltage to starter relay and ignition module. Wiper IA has no output. As I thought, this type of switch is very difficult to understand.